Okay, so this is going to be 2.3. We're going to go through 3 of these problems. We're going to start with number 7. Okay, we've got an 81 kilogram. Now that makes it a mass. So 81 kilograms is the mass of our baseball player. Kid's going to slide into second base. The coefficient of friction between the player and the ground is, my heck, I cannot win with this. I keep moving it. Okay, it's 0.49. So that's the coefficient of kinetic friction. So mu sub k is 0.49. That doesn't have a unit. And then what else we got? What is the magnitude of the frictional force? So how big is the friction? And if it's rest after 1.6 seconds, so the t would be 1.6 seconds, what's the initial velocity? So we're being asked for v naught. We're also being asked for the force of friction. Okay, those are our 2 things we're looking for. Well, let's go in and start talking about how we're going to get there with that information. Okay, so first thing we need to understand is what's going on with our person. So we're going to talk about different things that are going on. We know that the player has a weight that's going down and a normal force that's pushing up. Because they're on a horizontal surface, we're going to assume that those should be equal and cancel out. Assuming that the runner was going from left or going from right to left, because they're running from first to second, friction is going to pull back on them as they slide. And so that'll slow their slide towards second base. So we know that the normal force will equal mg because they're gonna have to cancel each other out, right? So this force and this force should cancel. What that means is that the sum of the forces in the problem is just going to be the force of friction, which will equal ma. That's an afterthought, right? This equals this. We've still got to deal with the force of friction before we can solve more information about it. Okay, so don't get too carried away with that yet. The first question we're asked is, what is the frictional force? Well, we know the definition is the coefficient of friction times Fn, but we're told in this problem, because of the setup, that Fn and mg are going to be the same. So this would be mu sub k times mg. Well, mu sub k is our coefficient of kinetic friction, which would be 0.49 times the mass of our baseball player, which is 81 kilograms, times gravity, which of course is 9.8. If we grab our calculator, we throw those in there, we've got 0.49 times 81 times 9.8. Whoops, yeah, that's right. We get 388.962. That's going to go to 389. So the force of friction should be 389 newtons. It might have it as 390, but I'm just going to go ahead and go with the 3 sig figs. Truthfully, if I look at the numbers, that's 2 sig figs, that's 2 sig figs, that's 2 sig figs. So this really should be 390 newtons if we're being really thorough. Sometimes I get shortcutty, I try to just jump too quick. Should be 390 newtons. Then, given that, we want to try and find out the initial velocity. When I'm asked for an initial velocity and I have things like time, it makes me think of kinematics. So if you start thinking about the kinematics, you have v naught, we want to know. V, well, this guy is sliding. We assume that he comes to a stop, so 0. Acceleration, I don't know. Delta x, I don't know how far the person slides, but I know it takes them 1.6 seconds. Well, I need to know at least one more thing in order to find my initial velocity. All of the kinematics require that we know the acceleration, so we might as well try to figure that out. Well, right up here we have the force of friction, which we know is 390, equals the mass times acceleration. So I can use this information to find my acceleration. I'm going to use the 388.962. Now I don't want, the reason I'm doing this is I don't want to propagate error through the problem. So I always want to use the least rounded values for as long as possible. Because of that 390, I'm still going to do some calculation with it. I don't want to mess that up. It equals the mass of the baseball player times their acceleration. So if I divide by 81, the acceleration that the player experiences during this period of time if I divide that by 81, is 4.802. And so I can have 4.802. Now if I'm looking for a kinematic that doesn't use delta x, I get the first one. V equals V naught plus AT. V being 0, my A. Now this is one of those things where when we use F equals MA, you don't always acknowledge whether it's positive or negative. The truth is I was slowing something down. I really should use a negative 4.82. Because if I, sorry. If I don't use a negative for A, then V naught's going to come out negative, and that's okay, but we have to understand what we're looking at, and what are we going to want to communicate to someone else. We're going to tell them that they had a positive initial velocity. I'm just going to go ahead and this number, I'm going to acknowledge that when I move it over, it's just going to become a positive, right? You're going to add it over. So whatever that number is, it should be my answer for V naught. So grabbing again our calculator, take that number times 1.6, we get 7.68. We're going to go ahead and say 7.7 meters per second would have been their 2 sig fig initial speed. And they did the 7.68 and 389. Again, I feel like all the numbers we were given were definitely 2 sig fig numbers. But anyway, number 9, we have a wooden crate resting on the floor. What's the maximum amount of force you can horizontally apply to it without it moving? And then if you continue to exert this force and the crate starts to slip, what will it accelerate at? So when we start this, we have to start it with an understanding that we've got our wooden crate. It's got a mass of 120 kilograms. Okay, mu s is 0.5, mu k is 0.3. We want to know, yeah, that's pretty much all we have. So we should need. So we talk about again our options. There's mg down, fn up, and we're going to apply a force.
Please pardon the interruption. Will you please release all volleyball players? Thank you.
We know that there's a force of friction that's going to oppose us. Now if I don't want it to move, that means I'm dealing with static friction. That would be the non-moving. And what that means is that my force of static friction would have to equal my applied force. If they're equal, then I'm not moving. Okay, I won't get it to budge. And so I know, based on the fact that it's a horizontal surface, that Fn is mg. And so when I look at my force of friction, right, the formula for force of friction is mu sub s in this case times Fn, but we know that's mu sub s times mg. And that would equal the applied force that I'm allowed to get to. This is the maximum I can get before it starts to move. Where mu s would be 0.5 times the mass of the box, which is 120, times 9.8. This would be my applied force that would prevent it from moving. Any bigger than this, and it starts to slide. So we grab our calculator, 0.5 times 120 times 9.8. It's going to give me 588 newtons. So 588 newtons, okay? The box doesn't budge. 588.1, it starts to move. And so that's my don't move the box approach. However, if I exceed that, okay, let's say that let's go back to the way the question's worded. Okay, if you can continue to exert this 588 newtons on the crate when it starts to slip, right? So this is that tipping point. So we just give it a little extra nudge, and then we're pushing 588. What's going to happen to the box? Well, once it starts sliding, we know that the coefficient of friction is going to drop. So if you think about the diagram here, FA is now locked in at 588, but the force of friction has dropped because we're no longer not sliding. Once we start sliding, we get a lower friction. And so that 588 is not going to win. So when I do the sum of my forces in this x direction, the vertical is still normal force and mg, but when I do it in this x direction, okay, we have my applied force subtracting the force of friction. It's no longer balanced and equal to 0. Over here, they equaled each other, so subtracting would have given me 0. Here on this problem, it's going to equal ma. The box will accelerate. My applied force is locked in at 588 minus my frictional force will be mu k mg, and that equals ma. This is not a problem where you can cancel the masses because the 588 isn't linked to a mass. So we have 588 minus mu k, which is 0.3, times the mass, which was 120, times 9.8 for gravity, equals the mass of 120 times A. So once we do this subtraction, we're going to divide that by 120 to find how much I still accelerate the box after this box starts to slide. And so we're going to take our 588, we're going to minus 0.3 times 120 times 9.8 and get 235. So this is what's left over. Out of the 588 that I'm pushing, 235.2 newtons of force exists beyond friction. So this is more than what friction can manage. And so if I divide that by the 120 kilograms of the box, I get an acceleration of 1.96 meters per second squared. This box is going to continue to accelerate again and again and again until either I run out of room or until I can no longer apply that force. Eventually it might be going faster than I can run, and so I can't apply as much force. Okay, we've got one more last question I wanted to try and help you out with. It's our question with the skier heading down a 10-degree slope. That in and of itself is not too bad. I actually want you to do that part on your own. But I do want to help you with understanding how do we figure out what's the maximum slope, or what slope would create a balance, okay? Meaning, at what slope would the friction up the hill be equal to gravity pushing down the hill? And so if you can imagine, there's my 10-degree slope, okay? Call that 10 degrees. And here's the skier, okay? We talk about all the forces acting on it. You've got mg down this way. You've got Fn this way. And because we're going down the hill, friction will point up the hill. Now I'm going to go ahead and I'm going to call that positive, and I'll call down the hill negative, so, or down the hill positive. So I've got y sticking up and x going down the plane. It really just depends on how you want to draw it. The key idea here is if we're going to say that the skier has a constant velocity, then the skier has a balance of forces. There's no acceleration. That's what constant acceleration or constant velocity means. No acceleration, which means everything balances out. Okay, let me take that off for a second here. Okay, so let's make that a little bigger. There we go. Okay, so the idea here is we want to find some way to make sure that everything balances out. Well, remember these two vectors, mg cosine theta and mg sine of theta are still going to be part of it. In the y direction, we know that Fn will equal mg cosine theta. That's always true. And that's really helpful for when I do frictional stuff. Now, in order for me to have a constant velocity, I also can claim that the F of friction, the force of friction, and mg sine of theta have to equal each other, because then they would cancel each other out and there would be no speeding up or slowing down. And so we would have that the force of friction must equal mg sine of theta. Now there's more than one way to get to this. We could also have done this a different way, but we're gonna work our way there slowly. Okay. Those are a couple of things that we can claim. I'm actually going to come back and we're gonna approach this one a little bit differently. I think that that's going to get you some confusion. So let's step back and look at it from a different perspective. Let's do the sum of the forces in the x direction. That would be along the surface. Okay. I'm going to have mg sine theta going down the hill being positive. mg sine of theta. I'm going to subtract the force of friction. And if I have a balance, that equals 0. Now I could technically write ma here, but to get a constant velocity, a equals 0. So that's going to end up equaling 0. And that's how we got the force of friction equals mg sine theta. And that's totally doable, totally good. But I want to just go ahead and do the substitution for force of friction right away and then solve. I get mg sine of theta minus, now remember the force of friction is mu sub k times the normal force. But the normal force is mg cosine of theta. And that all equals 0. A couple things we can notice right away. Okay, mg exists in everything, and over here you can divide 0 by anything. So I can actually cancel out m and g. What's really cool about this is it has nothing to do with what planet you're on. If we go to Mars, the same rules apply as they do here on Earth in terms of coefficient of friction for that planet. It's still going to work. And so what I have left is that the sine of theta minus mu k cosine of theta equals 0. This becomes really complicated to solve if I'm trying to do it by, let's zoom back out. Here we go. Okay, if I'm trying to solve this by using some sort of trig secret, it's going to seem complicated. So we're going to be really specific about this. I'm going to start by just trying to do the basics. I'm going to go ahead and add mu k cosine theta over to the other side. I don't like the negatives. Let's get mu k, which is a known number, over on the left, or on the right. I now have sine of theta equals mu k cosine of theta. Now, this is where the magic does happen. You have to know a little bit about trig. Here's what I see. I'm looking for theta. We got to remember, we're looking for angle theta here. What's the angle where we get a perfect slide, where we don't speed up or slow down? I can't have theta on both sides of the equal sign. So I ask, how do I get theta moved over? Well, theta's trapped with my cosine, remember, and with my sine. So I have to move the cosine with it. So I'll divide by the cosine of theta. Now some of you maybe could have thought of this before based on your Algebra 2 and pre-cal, but this is kind of where we get to. For any coefficient of kinetic friction, the critical angle when there's no acceleration is sine over cosine, which we remember from our previous classes is the tangent of theta. Sine over cosine is tan. And now if we put in our mu sub k, which with the polished wood against, or waxed wood against snow, we get a 0.1 equals tangent of theta, which we're going to take a tan inverse of the 0.1 to get theta equals, whoops, wrong button. Theta equals, I need my calculator, what am I doing? All right, here we go. Turn that on, second tan, 0.1 is 5.71 degrees. Now that is only part B of this question. I still want you to answer part A on your own. But if you go over a 5.71 degree angle of incline, you're going to speed up as you go down the hill. And that's a pretty interesting thing. One of the things that's really important about this exact question, okay, is that if I find out the mu of sliding friction for a car tire against asphalt or concrete, it sets the maximum angle that a road can be built at. Can you guys imagine for me with me real quick? If you build a road that goes up over a mountain, and if you can imagine right here maybe is where we have a steep angle of incline. If that angle is too steep, okay, my car will have its wheels start to spin against the concrete and not maintain traction or friction against the ground, which means I might think I'm going to go up the hill, but I can't physically go up the hill. And coincidentally, on the way down, if I were to try and stop, my car would continue to slide down the hill and I'd be uncontrollably into an accident. Which is why there are times when on icy roads, we see cars that just seem like they can't stop. Literally, their coefficient of friction is dropped too low for the angle of incline. And it is physically impossible for them to stop. So that's a really, really interesting question. Maybe we'll get into class a little bit. What is the maximum angle we can build a road at and still manage to have the average car climb that hill? All right, that was a longer one, but good luck. We'll see you in class.